And we're back with our next podcast on Twisted Pair. We left off talking about solid and stranded conductor wire for Twisted Pair. Just reminding you, solid conductor Twisted Pair cabling is going to get used for your horizontal cable run, and the patch cables on each end are going to be the stranded conductor. Important, important. As we move on to the next characteristic of Twisted Pair, we talk about the outer insulation. The outer insulation or jacket is constructed of different materials for different uses. There's three main types that you're going to encounter: general purpose, riser, and plenum rated. The general purpose is for just basic use like patch cables. The riser rated you would encounter going between floors, one data closet right through the ceiling up to the data closet above it, or plenum rated, where I would actually have this installed maybe above ceiling tiles in the hallway. Plenum rated cabling for plenum spaces. Now, your general purpose cable, the outer jacket insulation, is typically PVC, polyvinyl chloride, or some derivation of that. It is flexible, so it's used for patch cords, that sort of thing. Typically stranded wire for patch cords, and it's used where flammability is not a disadvantage, where it's not if there was a fire in this room, it would be contained in this room, if you will. The typical code I'm going to find on the outside of the jacket, again, when we look at the outside of a cable, there's always some kind of code on there saying things like the manufacturer, the category, what standard, etc., etc. And then in there is usually a little code that says something about the type of insulation it is. And on Twisted Pair, we're looking for codes like CMG or MPG. And the key here is looking at that last letter. CMG is general purpose, or MPG is general purpose. The G is telling me this is general purpose cabling. So I'm looking for that code on there to know this is rated as patch cable. I'm not going to install this above the ceilings or anything like that. That'd be the code on the side letting me know it's just general purpose cabling. Start looking for that, be able to find that, be able to identify that. The next cable you might run into for Twisted Pair, the next type is your riser rated. The outer jacket insulation is usually some type of slow smoke polyvinyl chloride. This is typically solid wire conductor, and this would be typically used between floors. Again, connecting this data closet to the floor right above me to the data closet above. I could use riser rated cable for this, where flammability is a bit of a concern. The concern here is if there's a fire in this, in data closet A, it could potentially travel up through, via the cable up to the closet above. So riser rated cabling would be used between floors like that. So on this type of riser rated cabling, I'm looking for the code, and again, I'm looking for a code like CMR or MPR. And the key here is, again, CMR, the R telling me riser, or MPR, the R is telling me riser rated cabling. So I'd be looking for that particular code on the cable. The last type you might encounter is your plenum cable. And the outer jacket insulation, again, is another type of low smoke polyvinyl chloride. Sometimes it gets into a little more specific, where polyethotetrafluoroethylene or something like that, where it's more like a Teflon kind of material. This is typically going to be used with solid wire, used in plenum spaces. Again, plenum space, if you look again here, plenum space is that airspace above the ceiling that's used as part of ventilation in a building. If I'm installing any cabling in that kind of space, it needs to be plenum rated. It's in a plenum space. So my code on my jacket is typically going to be a CMP, MPP, and again, pay attention to that last letter, CMP or MPP. The P on the end is telling me plenum rated cabling. Again, be able to recognize that, be able to identify that if you're looking at a cable. MPP, CMP, plenum rated cabling. That's the next characteristic of twisted pair cabling, that outer insulation. The next characteristic we run into with twisted pair cabling is the twisting. Well, let's first talk about, kind of the why, and then we'll get into the detail of differences. Wires are twisted together to reduce the effects of electromagnetic interference and crosstalk. Okay. When I look at these wire pairs, they are twisted together. It is a pair, and as we said before, if I look at the green pair down here, white, green, and green, white, green would be sending signal one direction, green would be sending it the opposite direction. When they're paired together like that, they're trying to cancel each other out and kind of become a balanced system, if you will. Well, let's take a little more look at this. Here's an example I have. If I just had an ordinary cable, and the wires aren't twisted, if you will, and they're just two wires laying next to each other, this is trying to show you green, and red. Green would be sending data this direction. Red would be sending data this direction. Well, if I have a magnetic field, as the magnetic field comes by these wires, if you stop and think real quick, let me pause and kind of get you thinking this direction real quick. If you've ever taken a wire, wrapped it around a nail, and hooked it up to a battery, when you hook it up, that wire wrapped around the nail makes a little electromagnet. So the phenomenon here is electricity moving through a coil of wire is producing a magnetic field. If you take a magnet and move it by a wire, I'm going to get the opposite effect. If I take a magnet and move it by a wire, the magnetic field is going to grab electrons in the wire and try to, grab them and throw them down the wire. I'm going to try to get current flow. That's how electricity is made for your house. That's how the power company does it. They move magnets around coils of wire, and when they do, they start grabbing electrons and throwing them down the wire and make electricity. So if you have that kind of in your brain now, electricity moving through a wire makes a magnet. A magnet moving by a wire can make electricity. Those phenomenon go together, if you will. If I now apply it here, where these blue lines are magnetic fields from some electrical interference, maybe a motor running or a photocopier running or something in my data closet that shouldn't be there. Again, motors, photocopiers, microwaves, that kind of thing. If I have this magnetic field moving by my wire, what it's going to do is induce current. It's going to get a little bit of a current flow going. And what they're trying to show you with this picture is this magnetic field goes by this red and green wire. It's inducing a little current this way. It's inducing a little current this way. And I'm getting current flow going in each direction. It's going to be in the form of noise. If I take my wires and instead of just laying them straight, I start twisting them together, and that's what the green and red wire they're trying to show you down here on the bottom one now. If I start twisting the wires together in pairs, take my wire pair and twist them together, when this magnetic field comes by, let's just examine this far right blue arrow here. As this magnetic field comes by the green wire, it tries to put a little current this way. As it goes by the red wire, it tries to put a little current this way. Okay. Well, if I examine the magnetic line next to it, this one is trying to put a little current into the red wire going the opposite direction, and a little bit of current into the green wire going the opposite direction. So this little bit of current here cancels this current. Just by the sake of twisting these wires together, any magnetic interference or noise nearby almost cancels itself out because of the wire twist. It's pretty awesome. So just by twisting these wires together, I'm kind of doing a little bit of shielding from noise nearby. It's not honest to goodness shielding, but it's kind of, because I'm making a balanced circuit. So it's extremely important that these wires maintain their twist. As soon as I start untwisting them for termination, I'm opening them up for the kind of noise or interference I got in this top example. So these wires being twisted together is really important. And if I now look at back when we talked phone wires earlier, a typical phone wire termination goes into a block like this. Look how much wire untwist is here. Oh, that's horrible. Well, the screw type termination that I'd have on a phone block was acceptable back in the old category 2 and 3 days, if you will, suitable for phone, but this is not suitable for data terminations. What's suitable for data terminations is an insulation displacement connector. Insulation displacement connector, as I lay the wire into this outlet jack, if I were kind of zoom in on this outlet jack down here, I see a metal V in there. That's what this part here is. As I lay the wire into this and I force it down with my punch down tool, as I punch it in, the metal V is cutting the insulation away and making contact with a copper wire inside. Well, because of that, if you take a look, I got my wire pair coming in here, boom, boom. There's almost no wire and twist here on this green pair and the brown pair. I have a lot less wire and twist for this type of termination. I use an insulation displacement termination. Really important. That reduces the amount of wire and twist that I need for this. And the same is true for my patch cable. As I strip the insulation off of this a piece of Cat5, if you will, and slide the wires into the connector, okay, you slide the wires in here, this little brass pin at the very end has little teeth on. When I crimp it, those teeth get forced up into the little teeny wires, cut the insulation, and these brass pins make contact with the wire inside. Again, another type of insulation displacement connector. All necessary to have a termination with twisted pair with very little wire and twist, and helping with that issue. All right, the next piece of this, because again we're still working our way towards categories of cable, the next piece of this puzzle they start talking about is impedance. They start saying that according to your standard I should have, I think they mention it up here, actually let me go way back here to the approved types real quick. We'll go back to our approved types just so we can see. Here's our approved types of cabling. 100 ohm balanced twisted pair cabling. Well, 100 ohm is one of our next characteristics. If I look at my categories of cable and look at the impedance column, every single one of these says 100 ohm, 100 ohm, 100 ohm, 100 ohm. Okay, let's make a little sense of this 100 ohm thing. This plays into the wire twist, so hang in there with me. When they say impedance, this is what they mean. The impedance is the total resistance and reactance offered by a component. Well, impedance, if I look at the mathematical formula, you don't need to know this formula. I'm just doing this for information purposes. But if you look at the mathematical formula, I have resistance squared plus x sub L minus x sub C squared. X sub L is your inductive reactance, your x sub C is your capacitive reactance. So I factor those two together, square them, add them to the resistance, square them, and then I take the square root of it all. So I'm factoring together all kinds of things to get my impedance. Okay? Now, why is this important? The max amount of power is transferred when the impedance of the source and load are matched, thus giving my max cable distances. Any mismatches cause reflections. So anytime I deviate from this 100 ohm impedance across my data network, I'm going to get micro reflections. It's going to reduce the effective length of my cabling. So if I look at my formula a little bit further, again, all information purposes, you don't need to know these, but if I look at the formula for inductive reactance, I look at the formula for capacitive reactance, what I find in here, 2 pi FL, 1 over 2 pi FC, okay, what I start finding is a common factor of F in all these, okay. I mention this because if you look at these, they all have F for frequency in the formula. As the frequency increases, this now upsets the impedance of the cable. Well, increasing frequency is part of increasing bandwidth. If you take a look here, we keep increasing our frequency to get more bandwidth, if you will. Well, as I start increasing frequency, this is going to throw this off. It's going to throw this off. It starts throwing things out of whack. So, how is the impedance rebalanced to maintain the 100 ohms required by the standard? Well, the structure of the cable has to be adjusted to rebalance the cable to maintain the 100 ohm impedance and the 100 meter cable distance. Thus, the categories of cable have been created over the years. So, to keep this 100 ohm impedance for maximum data transfer, if you will, as they've been increasing the frequency to send more data, we've had to change the structure of the cable, new categories of cabling, to meet that need. And this goes right back to the whole twisting thing. All right, in the next podcast, I'm going to start exploring these categories of cable, and we'll talk about that just a little bit more.